In this video, we're going to talk a little bit about the theory behind k-means. Why does it work? Why is it a valid clustering algorithm? But also why it can be inconsistent and why it isn't always the best clustering algorithm to use. So here's an example of running k-means on the same data set as before, but this time we've set the k value, the number of clusters, equal to 4. And you can see this is the output that we got. However, each time we run k-means, it's possible that we get different outputs. We get different clusterings. For example, here's 3 different cases where we ran k-means. And in each case, this was the optimal clustering as returned by the algorithm. And you can see that they're different. These two over here are slightly different. This one over here is pretty weird. Notice that the red cluster is kind of spanning this gap here, with like one red point over here and a few down here. But in all 3 cases, what happened is the algorithm converged. The algorithm stopped. And yeah, this was the result of running k-means. So how do we figure out like what a good clustering is? Like how do we determine which of these is the one that we should go with, that we should use? How do we quantify how good or how bad a given clustering result is? Well, one thing we commonly do, and we've done a bunch of other times in this class, is come up with some sort of loss function. So my question to you on this slide, I want you to pause and think, is, well, what loss function do we come up with? How do we define how good or bad a clustering is? What are the components? What are the terms in this loss function? So pause, think about it. 1, 2, 3. Hopefully you paused. Maybe not, but in any case, I'll continue. So when this lecture was originally given in fall 19 by Professor Hug, he asked the class for ideas. There are a couple ideas. One was that we somehow need to look at the sum of distances from each point to its center. So this is a pretty reasonable idea. If you think about it, if we have points that are all very close to their center, then that means that our clusters are very compact. Our clusters make sense. But if our points are really, really far apart from their center, for example, this point compared to this point, then that's bad. And we don't want that to happen. And that would be an indicator of a worse clustering. Something else we can look at maybe is look at the balance between the number of points in each cluster. So in these two here on the left, it looks like each cluster has relatively the same amount of points. But in this one here on the right, this red cluster only has 4 or 5 or maybe 6 points, whereas the other ones have 20, 30 points. And maybe that's an indication that our clustering isn't the best because we have this imbalance here. So there's actually 2 common loss functions. One is inertia. So what is inertia? Well, inertia we define as the sum of squared distances from each data point to its center. This is actually very similar to what this student came up with, except we're just squaring the distances as opposed to summing them. So you can see here on the slide, here we have 7 points, which we've clustered into 2 clusters, blue and orange. You can see the centers are the stars again. And we've labeled this plot with the distance from each point to the center. So this blue point here, it's 0.19, whatever, away from the center. This orange point here is pretty far away, it's 0.58. And what inertia does is it just sums the squares of all these distances. There's also this other thing called distortion, which is very, very, very similar to inertia. Except what distortion does is it weights these distances based on how many points are actually in each cluster. So with inertia, remember in this cluster we have 4 points, and in this one we have 3. So in inertia, this orange cluster is going to have a slightly larger impact, a slightly larger bearing on our loss function, simply because it contains more points. Whereas what distortion is going to do is it's going to give each of these clusters kind of equal weighting. So the way we do that is we just divide each term based on the number of points that are in that points cluster. So for example, for the blue points, we'll divide by 3. So divide each of these square distances by 3. And for the orange points, we'll divide each of them by 4. But otherwise, it's basically inertia, just with this weighting introduced. So each time we run k-means, again, here are 3 different outputs. And it turns out that this one over here on the left has the lowest inertia out of the 3. So this one was 44.96, this one was 45.95, and this one was pretty terrible, 54. And this makes sense. Like this goes along with what we've been saying. These 2 clusterings over here, they look pretty similar. You can't really distinguish them. And they have similar inertia. This one is marginally better, but maybe we weren't able to see that. This one over here is pretty bad, again, due to this weird red cluster, and its inertia was obviously worse than the other two. But what's important to realize is that k-mean stopped at each of these three spots. So like this time when we ran k-means still thought that this was optimal. So yeah, it's kind of one of the pitfalls of k-means is that you might end up with a really crappy clustering. And it turns out an actual like common strategy to get around this is just to run k-means a bunch of times and pick the one that has the best inertia. So in this case, we've run it 3 times. When we get we would probably pick this clustering. But maybe there's another clustering out there that has even better inertia. So maybe we would run 10 or 100 or 1,000 times even and pick the best one. And that's actually the default in sklearn as well. One of the parameters when you make your sklearn k-means object is that it'll do k-means a bunch of times. The number of times is a parameter that you can give it, and it'll return the best one. So yeah, k-means, if you just run it once, you might end up with a really crappy clustering. Well, why can we end up with bad clustering, so really high inertia? Well, k-means is trying to minimize inertia. That's the objective function that k-means is trying to minimize. However, it doesn't really work all the time, as we just saw, as I just explained. So when you think of k-means, you can think about it as 2 kind of minimizers, 2 optimizers that take turns. So what the first optimizer is going to do is it's going to hold the center positions constant. So it's going to say, okay, given my stars are here and here, or here and here, wherever they are, what's the best coloring? What are the best labels to assign to each of the points, given that these stars are fixed? The second optimizer, what that's going to do is it's going to say, it's given that these points have the colors that they do, what are the best centers? Where should I put the centers to minimize the distance? So that's what the second optimizer does. And both of these optimizers take turns, and they both kind of go back and forth, and neither one really overtakes the other. And that's why in some cases you end up converging at a really bad spot. You can kind of think of these bad clusterings, for example, this one, as like a local minimum. K-means ended up here, it stopped, it reached a local minimum, it thought it was done, but I mean, really it shouldn't have been, right? Because there's other better clusterings out there. K-means just wasn't able to get there. So yeah, this would be like a local minimum of inertia. Okay. So another kind of thought experiment for you is to come up with an algorithm that optimizes inertia. What your algorithm needs to do is return the exact best centers and colors 100% of the time. K-means, as we saw, obviously doesn't work 100% of the time. So what your algorithm needs to do is work 100% of the time. And don't worry about how long it's going to take. So this is a pretty hard question. It's an algorithm-based question, 61B, 70, 170. I actually haven't taken either CS70 or CS170. But in any case, maybe think about it for a second. Again, could be a really, really challenging problem. And yeah, pause the video and come back. Okay, hopefully you paused. And here's a possible algorithm. So what we're going to do is we're just going to iterate over all possible combinations of colors, all k to the n possible colorings out there, and just pick the best one. We'll iterate through. If we find a coloring that has a better inertia, a clustering that has a better inertia, then we'll just store that, keep track of it, and then keep trying to find a better one. There's actually no better way to do this. If we wanted to do it perfectly 100% of the time, it would take on the order of k to the n running time. And k to the n is a really, really large number. For example, maybe we just have k equal to 2, but we have 100 data points. Well, this algorithm would have 2 to the 100 iterations, which is absurdly big, not possible to solve. So it turns out, for those of you who have taken an algorithms class and know about P and NP, turns out the k-means is NP hard. It's just really not feasible to solve exactly in a reasonable amount of runtime. So yeah, the only thing that will do it exactly is this kind of brute force search, which will take a really long time And that's why we have this other algorithm called k-means that will get us there pretty quickly, but it might not always work 100% of the time. And yeah, that's it for that video. And I'll see you in the next one.